Hello, everyone. We appreciate you taking time to join us today. Microbial Insights is delighted to have two very experienced speakers. We have our own Dr. Sam Rosolina and Dr. Alan Jeffrey, who are going to be talking to you today. They're going to be co-presenting about ways to incorporate CSIA analysis and petroleum forensics tools into site assessment that can result in better source distinction. Dr. Alan Jeffrey is a consultant in the environmental forensics in San Marcos, California. He has over 30 years of experience in U.S. and international work with environmental and petroleum geochemistry. Much of his work has focused on the use of geochemical and stable isotope techniques to solve environmental problems, including sources of spilled hydrocarbon fuel and chlorinated solvents, and methane seeps as well. He has written over 300 proprietary reports providing interpretation related to hydrocarbon and chlorinated solvent releases. He's been retained as an expert witness in over 50 litigation cases and has been deposed and testified at trial in several of these cases. He's also given numerous presentations on environmental forensic techniques and case studies using these techniques in platform presentations and workshops in North America, Europe, and Australia. So we're thrilled to have Alan with us this morning. And then we also have our own Dr. Sam Rosolina, who's the director of the CSIA laboratory here at Microbial Insights, and he does a spectacular job of being sure that not only does the CSIA data that we generate here meet the highest quality standards, but that the end user truly understands the data and how best to apply it for site management. Sam graduated from the University of Tennessee with a PhD in analytical chemistry, and he was an adjunct professor of general chemistry at the university prior to joining our team here at Microbial Insights. So we're delighted that you guys are joining us today. Please note that this webinar is being recorded and will be available in the resource section of the Microbial Insights website within the next week. You don't have to contact us. A link will automatically be emailed to anyone who registered for the webinar. After the presentation today, we're going to have a short question and answer session. So if you have questions for Alan or for Sam, feel free to go ahead and type those into your GoToWebinar software, and we'll answer them, as many of them as we can get to at the end of the presentation. So without any further ado, I'm going to go ahead and turn it over to you, Alan, to get started.
Okay, thanks, Dora. Good morning. What I would like to do in this presentation is give you a short overview of what CSIA actually is, and then move on to show how it was used in certain case studies, looking at the releases primarily of chlorinated solvents, because back in the day, 10, 15 years ago, most of the emphasis was on looking at dry cleaning sites and chlorinated solvent releases. I'll start with a little short review of isotope geochemistry. My slides are not advancing here.
So Alan, if you click off the presentation and click back on, can you see if that will? Okay, I can see your cursor moving now. Will your slides advance?
Yeah, I'm not sure why it's. This is a problem we had the last time. Let me. Okay, let me. Okay. Okay, let me pull up. Oh, okay. Dora, is that showing now? Carbon isotope page?
No, and I'm not. Let's see. Let me see if I make you the presenter again, if that'll work. Okay, see if that'll let you show your screen.
Hold on a minute. Let me show my screen.
There we go. Yep, that's it.
Can you see my screen there?
I can, and we're on the carbon isotope page now that we can see that.
Okay. Apologies for that. The technology sometimes gets the better of us. Anyway, a number of elements in nature have several isotopic differences. Carbon, for instance, has 6 protons, 6 neutrons, and mass 12. Mass 13 has an extra neutron, and mass 14 has 2 extra neutrons, which make it unstable and radioactive, and that's the basis of carbon-14 dating. Still not.
So, Alan, would you like me to take control back, and then you can just tell me when to advance?
Yeah,
Does that work?
I think we might have to do that, Dora.
Okay, sure, no problem.
Okay.
Actually, Sam, can I have you do that, because I don't have the slides pulled up on my screen?
That's no problem. Okay.
Sorry about this, everyone. We should be good now, and you can advance slide. All right, sounds good.
There we go. So these are the approximate global abundant isotope ratios for certain elements that are useful in geochemistry. Most of them, the heavy isotope is in the minority. For carbon, it's carbon-13 is approximately 1% of all carbons, and most of them are very small compared to the lighter isotope, except for chlorine. Chlorine-37 is about a quarter of all the chlorine atoms. And the main thing in this is there are small variations in the ratios caused by source, and also the source that they're coming from, and also chemical and biological transformations. Next slide, please. And this is the terminology for stable isotope ratios, the delta values, and for carbon, this is defined as the carbon isotope ratio of the sample minus the standard, and there are a number of international standards used for each element, divided by the standard, all multiplied by 1,000, and the results are shown as delta values in parts per thousand. And by convention, enrichment of the heavy isotope relative to the standard is given a positive value. Enrichment of a light isotope relative to the standard given a negative value. And this explains why in many cases, especially with carbon isotope ratios, the delta values will be negative, which kind of confuses environmental regulators and other environmental studies, because negative numbers don't really mean much to most people as far as this is concerned. Next slide, please. Here are some of the standards, international standards that are used. For carbon, it's a PD belemnite, and then standard mean ocean water, air nitrogen, Canyon Diablo triolite. Triolite is a sulfur mineral, and chlorine, standard ocean chloride. Next slide, please. There are 2 types of looking at isotopes, stable isotope ratios. Bulk and compound specific, 2 ways of analyzing them. Bulk ratios are the average of all of the carbon atoms in a material. For instance, all of the hydrocarbons in gasoline, or all of the alkanes in crude oil. And they're altered little by biodegradation of the materials. And the reason for that is that biodegradation of something like a crude oil only changes the carbon isotope ratio of a small percentage of the compounds in a crude oil. The majority of the carbon compounds in there are unaffected by biodegradation, so they retain the carbon isotope ratio originally, or very close to it. Whereas in compound-specific isotope ratios, in contrast, we're looking at a specific compound in a material, for example, benzene and gasoline. And when biodegradation takes place, that can change, that can alter much of the benzene in that sample and then cause isotopic fractionation. That is a change in the stable isotope ratio. Next slide, please. This is a monograph published by the EPA back in 2008, which is a guide to how to use CSIA and how to set up projects like that. And I found it very useful, and I think it still is very useful if you're getting involved in CSIA. Next slide, please. A little schematic here of the equipment that's used in CSIA, a GC gas chromatography, isotope ratio, mass spec. So the compounds are injected into the GC. We separate the compounds we're interested in. So maybe benzene and toluene and gasoline. And for carbon, they go through a combustion furnace, converts the benzene and the toluene into CO2, and go through an interface and into the mass spectrometer, and the mass to charge 45/44 carbon isotope ratio is measured. Next slide, please. Oh, and the key thing here is that peak separation is crucial. You can't have overlap on the compound you're interested in, otherwise it will change the isotope ratio and complicate things. For volatile compounds, primary applications are chlorinated solvents, BTEX in gasoline, MTBE and additive in gasoline, and also hydrocarbon gases such as methane. The volatiles are isolated from the groundwater and soil on an SPME fiber or a purge and trap instrument, and then the volatiles are desorbed into the inlets of the GC mass spectrometer I showed before. Next slide, please. For non-volatile compounds, primary applications are crude oils, polyaromatic hydrocarbons, can also be done on nitrate, and some other volatile compounds. Oils and gases are then directly injected into the inlets of the GC mass spectrometer. For nitrate, the nitrogen and oxygen atoms of nitrate are converted bacterially to nitrogen and carbon monoxide, which are then inletted into the GC. Next slide, please. There are two primary uses for CSIA, and this applies to both chlorinated solvents and gasoline, diesel, other things. One is source identification. So different isotope ratios may indicate different sources. Ratios may indicate, similar ratios may indicate the same source. And that's really what I'm going to focus on this morning. But another aspect of usefulness of CSIA is the extent of biodegradation. And that can be calculated from the change in the isotope ratio during fractionation, which I'll explain a little bit later. Next slide, please. Okay, here we have the case studies. All of these are look at chlorinated solvent sites, because back in the early days of CSIA, when it started to become popular, one of the big issues was looking at dry cleaning sites where releases of chlorinated solvents had taken place. So these are all chlorinated solvent studies, but the principles are exactly the same whether you're looking at gasolines, MTBE, or other things. So we'll progress from some straightforward studies where there's little biodegradation or little evidence of biodegradation, and then move on to a couple of studies later on which are more complicated because biodegradation has taken place. And the last one will show the uses of the three isotope ratios that can be used with chlorinated solvents, carbon, chlorine, and hydrogen, and how they can be useful. Next slide. So the first case here is contamination in multiple aquifers. This was a site up in Northern California where there were several aquifers in the ground, and it was found that the upper and a lower aquifer were contaminated by PCE. That's PERC, or tetrachloroethene. There were only traces of TCE and cis-DCE. These are the daughter products of degradation of PCE. So apparently there was little degradation. So the isotope ratios would not be altered. And what we were trying to establish is whether there were multiple sources in the upper aquifer or differences between what was in the upper aquifer and the lower aquifer. Next slide, please. It's a little schematic here of the groundwater plume. There were 4 wells in the upper aquifer. Top one had about 260 ppb. The middle, which was the highest concentration, just over 1 milligram per liter, and then 2 in the southern part, the down gradient, 210 and 180. Next slide, please. This is the lower slide. This is actually the well MW2020A was actually completed in the upper aquifer and the lower aquifer. This shows that well in the lower aquifer with 140 ppb of PCE. Next slide, please. This shows the carbon and the chlorine isotope ratios in the upper aquifer. There's a fairly narrow range of carbon isotope ratios there, about 1 per mil, suggesting that it could be the same PCE in the upper aquifer. The chlorine isotope ratios, though, do show some differences. Next slide. This is the MW20A well. Again, this is a lower aquifer. This had isotope ratio of -27, and if you remember the previous slide, the isotope ratio, carbon isotope ratio on that in the upper aquifer at that was about -29 point something. So that's a significant difference in the carbon isotope ratios there. Next slide, please. And click again, please. Yeah, there we go. So that shows a schematic of that particular well. It was actually completed at three levels in the C zone, but very small quantities of PCE there. But it shows 180 in the A zone, 140 in the B zone, and this shows the difference in the carbon isotope ratios in particular, and also some differences in the chlorine isotope ratio. But I'm sure when this came out, the well driller was pretty pleased to see the differences in the two zones, because it wouldn't be the first well that had problems with completions and allowed contamination from one aquifer to migrate down to the other aquifer, but this established that wasn't going on. Next slide, please. And this shows all of the values on a XY diagram, the carbon isotope ratios, along with the error bars. And it shows pretty definitively that the lower aquifer has a different PCE than the others. There's some differences in the upper aquifer, but it's not really definitive. Probably what would have to be done in this case would be take more wells, take more samples, and see if in fact there's a consistent difference or similarity in the upper aquifer to determine whether it's one release or several releases there. Next slide, please. So in conclusion, some differences in the carbon and chlorine isotopes in the upper aquifer, possibly different sources, but there's definitely significant differences between the upper and lower aquifers in the same well, which definitively shows that they have the TCE in the aquifers have different sources. Next slide, please. This was a site in Los Angeles. It's a manufacturing operation, degreasers used on site, and TCE and some PCE in the groundwater. And we were trying to establish whether there might be off-site sources and on-site sources. Next slide, please. This is a little schematic of the site itself. The site we're interested in is the one with all of the green numbers on it down there in the lower part of the schematic there. And as you can see, there's quite a number of wells in that site. Next slide, please. And this shows the TCE carbon isotope ratios. And the thing I'd like to point out here is that in the upper part there's isotope ratios for a couple of wells that are actually up gradient of the site itself. The numbers there's a bit of a variety of numbers there. It's a range of about maybe 2 per mil, but it appears that one plume, and it certainly appears as if it's migrating from the north down onto the east side of that site. Next slide. And then we found some other TCE and some other wells, on-site wells here, with no indication of anything north of that. 2 wells with very different TCE carbon isotope ratios. Next slide, please. And this is a table here showing the actual concentrations and PCE, TCE, and cis-DCE isotope ratios, carbon isotope ratios. If we look at the ones in yellow there, you'll notice that they have both PCE, significant amounts of PCE and TCE in those wells. And the key thing here is that the TCE in those wells is more negative than the PCE in both cases. And this is a possible indicator of biodegradation of PCE. As I'll show in the next few slides, when PCE degrades, the TCE becomes isotopically more negative, the PCE becomes isotopically more positive. So both of those show indications, perhaps, of biodegradation, a PCE release that's been biodegraded. If you look at the other ones, the ones with no boxes around them, you see the opposite ratios. TCE is less negative than the PCE. And that indicates that there has been major TCE releases and perhaps a small amount of PCE as well. And the one in red there was up gradient and has a very low negative number, probably resulting from degradation. Next slide, please. So what we were able to conclude from all of this was we had 2 TCE plumes, an off-site TCE source that was migrating from north to south onto the site, onto the east part of the site, and then an on-site source down in the lower west of that site. Could be a PCE source that's been degraded, or it could possibly be a PCE release and a TCE release mix. We couldn't really tell from this data. And this study was way back in the early days when we didn't have the capability of doing chlorine isotope ratios, and that now provided an additional way to perhaps distinguish these plumes. Next slide, please. Okay, I've talked about degradation and how it's complicated and makes life difficult, really, in trying to identify sources. This is a cascade diagram here showing the degradation of PCE PCE will degrade to TCE, trichloroethene, and then predominantly to cis-1,2, dichloroethene, and vinyl chlorides, and then ethene, and then gets mineralized. And the numbers here show the rate of a particular process. Next slide, please, Dan. Yeah. And so as PCE degrades, the isotopic ratio changes. This is so-called isotopic fractionation. And the next slide will show the rationale for that. So in a chemical reaction, carbon-12 bonds are weaker than carbon-13 bonds. So in a chemical reaction, carbon-12 bonds break faster than carbon-13 bonds. The reaction proceeds to, my PC seems to be having problems now. Bear with me. There we go. So the reaction proceeds to completion. All of the PCE will go to TCE. We're not manufacturing elements here. So the isotope ratio in the product is the same as the starting material. If the reaction is partially completed, carbon-12 is concentrated in the product, carbon-13 is concentrated in the starting material. So the product, in this case TCE, becomes lighter, more negative, and the starting material, PCE, becomes heavier, less negative. Next slide, please. So if you have biodegradation going on, is it possible to try and determine what the original carbon isotope ratio or chlorine isotope ratio would be in the initial PCE in this case? And this formula here shows how it can be done. The PCE, more amount of PCE times the carbon-13 ratio, TCE, DCE, and then divided by PCE, TCE, and DCE moles will then give you a value for the initial PCE release. And the big assumption in all of this is that there's no loss of PCE, TCE, DCE, or other daughter products from the system. Otherwise, it's just not going to work. Next slide, please. This was a fairly complicated case. We had degraded PCE and TCE in multiple plumes. This, again, was a site in Los Angeles. So we had separate plumes with PCE, TCE, and cis-DCE, marked differences in the degradation within the plumes. There was no or very small amounts of vinyl chloride, so little apparent loss of chlorinated solvents in the system. And what we were trying to establish here was whether we had multiple TCE sources in the plumes and whether TCE in one of the plumes was coming from migration of another plume. And the next slide will show a map of this. And that shows a schematic of the plumes themselves, the TCE concentrations in the groundwater. And you see in the middle there's a large lobe. That's the main plume. Off to the east there was another lobe, which may or may not be a component of that first plume. So it may be different, or it may just be another part of that main plume. And then over to the west there's an isolated plume. And in between the isolated west plume and the main plume, a number of wells showed very non-detect or very small amounts of chlorinated solvents. So it was thought that there wouldn't be any migration, but we wanted to establish that. Next slide, please. This shows the TCE and cis-DCE concentrations in the main plume, and you can see there's obviously biodegradation taking place. That one well towards the west there has a very high concentration of DCE, coming from degradation of the TCE. Next slide, please. A couple more wells in the main plume, and the one down on the bottom right there actually doesn't have any TCE at all. It's all degraded to DCE. Next slide. Over towards the east there. There's a couple of other wells, smaller amounts, TCE and DCE. And then next slide. To the west, there's both PCE, TCE, and DCE in that particular plume. And one of the wells is dominated by PCE. So next slide, please. This shows the TCE carbon isotope ratios in all of these wells. And that's pretty obvious from that too, that there's been biodegradation taking place. Some of these number there of plus 3.5, you would never see in manufactured TCE. And also the numbers over to the east there, -8 and -1. Again, you would not find those in manufactured TCE. So those numbers come from biodegradation. And over on the west there, -39, again, that's out of the range of manufactured TCE. So extensive biodegradation has taken place in almost all of the wells here. So how do we reconstruct this? Next slide. Using the formula that I showed before, we can reconstruct the initial TCE. And this one here is in the main plume, LSB1, which was 80% TCE and 20% DCE. Next click, please, Sam. And so if we make the calculation for the initial, next click. For the initial TCE value, we come up with somewhere in the region of -28, -29 for the initial TCE in that degraded well. Next slide, please. In this case, it was a well that only had traces of TCE and almost all DCE. So click again. The MW3, the initial TCE was almost exactly the same as the current TCE, the Del-C13. Next slide. And in this case, all of the TCE had been degraded. So click. The initial TCE turns out to be exactly the same as the current DCE. Next slide. Click. Click again. Next slide, please. So again, we're calculating the initial TCE. Click. And next slide. Okay. That shows the main plume, the middle one there. So we're going to move over to the east now and look at those two wells in the east slide. So click, MW15, click again, LSB4, and click. Next slide, click. All of the slides now are shown, are all of the initial TCE carbon isotope ratios are shown, and how they were lines show how they were calculated, and it shows a definite difference in the carbon isotope ratios between the main plume and that eastern plume, showing that they contain different TCE. There's some variation within the main plume, but it's not clear whether that is significant or not. Click again. They moved over into the west plume, and this is a little more complicated because there's a DCE, TCE, and PCE, but the calculation is the same. Click again. And this is the other well, the GFH18. And when you put them all together, the current PCE carbon isotope ratios are very, very close together. And so the conclusions of that is that the isotope ratio reconstruction shows at least 3 chlorinated solvent releases: TCE in the main plume, a different TCE in the east plume, and PCE in the west plume, with no contribution from the TCE plume in the main plume. And the reason we can say that is that if there was any migration over of the TCE in the main plume over into the west plume, we would not expect to see the reconstructed isotope values for the PCE being so close together. If you've got migration of TCE with different carbon isotope ratios, you would get much more spread. So we're pretty confident that that it's a closed system over on the west side. Next slide, please. The final case study here is a site with multiple PCE and TCE sources. And one of the wrinkles in this was trying to establish whether the TCE in one of the wells was from degradation of PCE or from TCE release. Next slide. This shows the site itself in New York City. Shows the PCE concentrations in black and TCE in blue. So over towards the east there's a couple of wells with only PCE, and another well with PCE and a smaller amount of TCE. Over towards the west, there's one well towards the top there with over 7,000 ppb of TCE and non-detect PCE, and then another well with 110 TCE, and then a lower well there with both PCE and TCE. Next slide, please. This shows the carbon isotope ratios of the PCE in the wells. There's a northern plume up there with carbon isotope ratios very close together, and then a southern plume there with a significant difference in the carbon isotope ratios, over 2 per mil difference there. So we appear to have 2 PCE plumes, and this was confirmed in the next slide with the chlorine isotope ratios. So the northern one has chlorine isotope ratios around actually the same number, minus 0.2 and minus 1.7 in the lower one. So both the carbon and the chlorine isotope ratios establish that we have 2 PCE sources there. Next slide, please. This shows the TCE carbon isotope ratios. And if we look at the one towards the left-hand side there, minus 36.1, again, this is a number that wouldn't occur in TCE, manufactured TCE. It comes from degradation of the PCE in that plume. And then over in the west there, back please. Over on the west there, there's 3 wells have very similar TCE carbon isotope ratios. The northern one there is obviously TCE because there was no PCE at all in there, minus 29. But the question that we were looking at was in the well with the minus 28.9 down at the bottom there. whether that was migration from the well north of that. That was in fact TCE that was a degradation product of the TCE in that well. And this is where the hydrogen isotope ratios really came into use. Next slide, please. So if we're trying to establish whether TCE and a PCE is from degradation of TCE or from a separate source, PCE, tetrachloroethene, contains no hydrogen, and the little ball, stick and ball diagram up there. PCE has 4 green balls for chlorine. When it degrades, one of the chlorines is replaced by a hydrogen. And what you have as a source of hydrogen? Groundwater situation. Apologies again, my PC is acting up. There we go. So in a groundwater environment, the only source of hydrogen is the water in the groundwater. So hydrogen degraded TCE comes from the groundwater. Hydrogen in manufactured TCE can have a very different hydrogen isotope ratio. It will depend on the process that's been used to manufacture the TCE. And so the hydrogen isotope ratios, in theory, can distinguish between those 2 processes. Next slide, please. And that shows the hydrogen isotope ratios. So in the red plume there, very similar hydrogen isotope ratios, and above that on the west side there, plus 400, a very different hydrogen isotope ratio. Now in the lower ones, we know that that well with the plus 68 number, we've established that the TCE in that well came from the biodegradation of the PCE. So we can be pretty sure that the one over at plus 55 also came from biodegradation. And of course, the plus 400 is a manufactured TCE. So we can, from this, it tells us that the TCE in that plus 55 well didn't migrate from above. And so there wasn't any contamination, let's say, of that well from the well further north of that. And next slide basically summarizes that. 2 PCE sources confirmed by carbon and chlorine isotope ratios. A TCE source we're on the west side with limited migration, and other TCE likely TCE degradation established by using the hydrogen isotope ratios. And I'll pass you over to Sam now, and I apologize for all of the works in the presentation.
Alan, that was great. Thank you so much for sharing some of those case studies. Throughout Alan's talk, he mentioned several times about things like manufactured ranges. He mentioned things like, said things like we wouldn't expect manufactured TCE to be within this range, or we would expect that TCE as a product, a fresh product, may be more negative than this range. And that kind of leads me to how do we know what these ranges are? Now, obviously, we can rely on professionals like Alan and myself to do the heavy lifting and look at this data, analyze it in the context of your site, and say, here's likely what's going on. But for you to make use of the CSA data directly, that's when we can turn to literature values. And since we don't all have access to those, that's why Microbial Insights has made this CSA database. So I'm going to do a quick walkthrough of this database, and hopefully you can see through the context of what Alan was talking about today, how useful this can be in terms of your own interpretation of CSA data. So again, why do we need a CSA database? Because interpreting this data requires some type of context. Now, a lot of that context is data that you already have. You know the groundwater flow direction at your site. You know kind of the differences in the geology and hydrogeology, different stratifications. You know what the history of your site is. But in terms of comparing that data that's on your report and saying, what does this actually mean? That's where the literature values come into play. And these literature values are not very accessible currently. They're either behind a paywall, or even if you have access to all of these, they're scattered throughout many journals, throughout a lot of different articles, and they're constantly being updated. So instead, what we now offer is anytime you perform CSIA through Microbial Insights, you automatically have access to our CSIA database. And within that, we have combined all of these different values from the literature. That includes manufactured ranges for carbon, chlorine, and hydrogen isotopes for a number of different compounds. And we'll show those in a second. It also means access to enrichment factors. This is the factor that relates the change in our delta value to the degradation that's taken place, to the fraction that's left. So these are key for getting the most out of your data. And of course, because CSIA is becoming more widely used, we, and I'm sure Alan can agree, we want to make sure that people understand kind of the limitations and the full use of CSIA. And so this is another important part of having access to this database to truly see what this means without over-interpreting your data. And then last but not least is simplicity. We, within this database, auto-plot a lot of the data for you. You have ways that you can change that around to make it fit what kind of questions you're trying to answer. So a quick run through of what this looks like from your viewpoint. When you log into this database, you have 3 different tabs up at the top. You have tables, you have a CSIA plots, and you have an example interpretation. So within the tables tab, what you get is kind of a summary table of the manufactured range of compounds that are specific to your project. So if you're analyzing cis DCE, TCE, and vinyl chloride for carbon and chlorine, then you can look at these values from the literature and say, this is the range that we would expect undegraded cis DCE to exist in, or this is the range that we would exist undegraded TCE to exist in. Similarly, a summary table of enrichment factors. We can look at the range of enrichment factors related to cis DCE degradation, for example, or TCE degradation. Now, further than that, we also give the actual references to these numbers, so you're not left out in the dark or making assumptions. You can actually find this data within the journals yourselves, and you have access to all of those as well. On top of that, with things like enrichment factors, what really comes into play is using this data to understand more about your site. So if you're curious about whether degradation is occurring at your site through biotic or abiotic mechanisms, then you can see whether these mechanisms are biotic versus abiotic. And if they are biotic, what organisms are at play? And same thing with our manufactured range. We have not only the actual delta values from the literature, but we have the actual references as well. So then when you go to the plot tab, I think this is the most fun portion of the MI CSIA database because we all love seeing data plotted for us. So within that, we have our standard mole fraction plot based on the VOC data that you provide to us. And this comes into major play whether you're trying to determine if degradation has occurred at your site, or if you're doing source delineation and you want to visually compare samples. You might say, well, MW7 has 11-DCE. Either that means there may be a different degradation mechanism at play, or maybe there's a different source at play because none of our other samples seem to have that. You can also specifically look at certain targets by clicking on those targets and identify those more clearly. Within the advanced options, you can select which compounds of interest as well as which samples you want to compare one to the other. So kind of the simplest start to our plots. Now we get into the context of CSIA. So Alan mentioned several times kind of a manufactured range that we would expect. This is the manufactured range for PCE. So if you were to select PCE for your delta 13C plot, you want to make sure that you select the right parent compound, which in this case is PCE. And within that, you're given the manufactured range of perchloroethene. And then you can directly compare your data and say, has degradation occurred? Or if you have a single data point and you don't know what the original delta value was, you can say, is it more degraded than our manufactured range? You can also, within the advanced options, include the 2 per mil uncertainty that the EPA recommends to take into account, and that adds on this 2 per mil bar. So then you can certainly say, this is conclusive proof that PCE is degraded at my site. Now, getting back to environmental forensics, Alan showed an example dual isotope plot. We can now auto plot this data for you if you perform dual isotope analysis through us. And this is that same site that I've been showing this data through. MW1 through MW6 goes from the source to the toe of the main plume, but there were some side gradient locations that were sampled as well, which were MW7 and MW8. And within this, we can see not only the manufactured range for PCE of carbon and chlorine isotopes, but we can see a distinct trend difference here between our main plume and our cross-gradient samples. And so this is a strong indication that there are 2 different sources at play. You'll note that both of these have kind of the same trend direction because they are undergoing degradation, which indicates they're undergoing the same type of degradation, the same mechanism. But the fact that they're far separated indicates that there is a source distinction here. Another very useful plot, especially for chlorinated solvents, is the modified Kuder plot. This takes into account the delta value, but it plots it against the mole fraction of the contaminant of interest. So in this case, if we're looking at PCE, we're plotting the delta value against the PCE mole fraction using these compounds in the calculation. And if we zoom in, we see that same separation between our plume, on-site plume, and our cross-gradient samples. Again, an additional line of evidence that there appears to be 2 distinct sources of PCE. Another very useful thing with the modified Kuder plot is that it's based on those enrichment factors. So now we can look and say, is our degradation due to biotic or abiotic mechanisms? In this case, you're looking at trends. So if we look at our abiotic trend, we see that it's within this pink range, very steep trend, but our data is going this direction. Our trend is showing a biotic degradation. So again, more useful information, whether you're looking at proving source delineation or proving degradation at the site and determining what is actively happening. We want you to take this CSIA database, utilize it the same way you would use Google every day, and truly add context to what's happening at your site. One other thing that many of you may have seen is that we are now offering all 3 isotopes, carbon, chlorine, and hydrogen, at the same price and the same turnaround time. Again, we have mostly talked about chlorinated solvents in this talk, but it's important to remember that this is extremely useful as an additional line of evidence for your petroleum forensics. If we're looking at benzene or toluene, for example, comparing those carbon and hydrogen dual isotope plots to get a true distinction between different samples. Extremely important, extremely helpful. If you have any questions about using CSIA for your site, or you're curious about more information, highly recommend that you reach out to us. We're happy to chat with you, talk through your site, understand more about what's happening, and kind of move forward with either helping with the sampling strategy or discussing whether CSIA might be right for you. And with that, I'll hand it over to Dora, and we'll see if we have any questions. Alan, you're still on the line, right?
Still on the line, yeah.
Great.
Thank you so much, Sam and Alan. That was an excellent presentation, a really good deep view of CSIA. We do have quite a few questions from the audience, so we'll get through as many as we can. The first one, Sam, might be a good one for you to talk about because I know you've researched this a little bit. Can CSIA be used for the perfluorinated compounds and 1,4-dioxane?
Great question, and one that we get often. So there are two things when we're talking about perfluorinated compounds, PFAS. Most CSIA in the industry is currently performed on VOC compounds. So we're looking at volatile compounds that we can pre-concentrate with a purge and trap, for example. So with that being said, PFAS are mostly non-volatile or very low volatility. Second of all, and this is maybe more important, is with PFAS we're looking at dual isotope if we're doing source distinction. But fluorine, unlike chlorine, only has one stable isotope, and we need two stable isotopes to do that ratio. So unfortunately, PFAS is currently unable to be analyzed by CSA. Now, 1,4-dioxane can certainly be utilized. The problem with 1,4-dioxane is it's, again, not very volatile, so the limit of detection is extremely high. We also see from the literature values that you get very little enrichment with 1,4-dioxane. So useful less to prove contaminant degradation, except under very specific mechanisms, but could be useful for source delineation.
One thing that we like with 1,4-dioxane, just as a follow-up on Sam, is we can do stable isotope probing, where we can do especially synthesized 1,4-dioxane, that's a heavy-weighted carbon, and we can load that onto our biotrap samplers, and then we can prove if that compound biodegraded. So it depends on the question that you're trying to answer about 1,4-D, but if you want proof of degradation, that is an option since CSIA is a little more complicated for that particular compound. Next question is for you, Alan. This question is about your experience in court. Is this diagnostic process accepted in court? Are they knowledgeable enough to absorb and digest this and be able to differentiate between plume origins?
Well, I haven't been involved in litigation issues with chlorinated solvents, I'm afraid. Most of my litigation experience has been with petroleum hydrocarbons, so I really can't comment on that too much. But I can give you one instance, a project, a case study that I haven't shown here, but it was in Florida, and it was a situation where the regulators believed that contamination down gradient at a particular site was coming from source A, let's say, and there had been a lot of biodegradation going on, and there was another site further up gradient that had some chlorinated solvent contamination, but the one down gradient was the one that the regulators were really worried about. But we were able to do the isotopic reconstruction, and it looked as if the initial, I believe it was TCE, the initial TCE isotope ratios most closely matched the one further up gradient, not the one that the regulators were really focusing on. And the regulators weren't ready to believe what we were saying, that the isotope ratios at the contaminated area came from the upgradient one, because there was no established migration pathway, and there were a number of wells in between the far upgradient one and the contaminated site, and they showed no chlorinated solvent shows there. So, and all of this work, and it's the same for petroleum forensics as well. The chemistry can tell you a lot, but you always have to take into account whether the migration could have happened. So even though the numbers are the same, if you can't establish a migration pathway from A to B, then the actual isotope ratios or the concentrations really don't mean anything.
That's great, and it's kind of similar to what we've seen, Alan, with the regulatory agencies too. Is that we have to make sure we're looking at multiple lines of evidence to understand the situation. And also, I think education is a huge component, and that's something that we're big on here at Microbial Insights. We try to do webinar education for both the consultants and the regulatory agencies on a regular basis, because there are benefits and limitations to each technology, and to do proper interpretation, we have to understand those. So if you're interested in a webinar, please reach out to Sam, and he can set something up for you on that. That would give you more answers to questions on these tools. Alan, this is another one for you. Can you talk a little bit about the noise that can be detected in the analysis, and how do you know if the ratio is a real difference or if it's just noise? And maybe Sam.
Yeah. Well, there are established error bars. The error bars that I showed in one of my slides, and that they're developed from analyzing standards and working out the error bars that way. And so that really is the key thing in trying to establish whether you're looking at two releases or one release, whether the error bars allow you to say this is the same PCE or TCE, or this is a different PCE or TCE. So that's the key determinant.
Great. Do you have anything to add to that, Sam?
Yeah, I think for those of you who are interested in kind of getting a deeper dive into the QA/QC of CSIA, Microbial Insights did a previous webinar called Making Sense of CSIA. It's in our webinars tab on our website, and we discuss in detail the importance of error bars, the importance of taking into account that error to truly, make sure that there are differences.
Great. All right, this one is a two-part for you, Sam. Can you talk, I know in the database we talked a little bit about biotic versus abiotic isotopic ratios. Can you talk a little bit more about the difference between those two? And then the second part of the question from the same person is, what's the cost for PCE and TCE on a groundwater sample?
Yeah, so for biotic versus abiotic, what you'll notice is that our trends here are based on, first of all, they're based on our carbon manufactured range, the width is. So you'll notice both trends start at the same location. But biotic has a much broader trend. It can be shallow, it can be sharp. And essentially what that means is if it's a sharp trend, that means we see a lot of change in our delta value with a very small amount of degradation. And what you'll notice is that for our abiotic trends, which is this pink, it's more likely to see that sharper trend than in biotic. So again, just like we've talked about multiple lines of evidence, you want to make sure that it makes sense whether you're looking at biotic versus abiotic. But often what we see, for example, if you have a ZVI barrier, you'll see these delta values increasing more sharply along the pink range rather than the blue range. So again, looking at trends is key. We always recommend looking at trends. You can't get this information from a single sample or a single snapshot. You can either sample temporally the same location over time and see which direction it's trending, or you can sample, from the top to the bottom of the plume and see which direction it's trending. Now, in terms of pricing, I'll let Dora determine whether or not we do that, because oftentimes, since this is going to be recorded, if pricing changes, we don't mention that on the webinar itself, but I'm happy to give you that information if you shoot me an email.
Okay, Sam, if you want to tell them what the current pricing structure is.
Yeah, so then in that case, if it's, again, same price for all isotopes, For a certain isotope like carbon, for example, the first compound is 500, and then each additional is 50. So if you wanted to look at PCE and TCE and cis-DCE, it's 500 for PCE, 50 for both TCE and cis-DCE, so that would be $600. And then if you wanted to add on chlorine for PCE, that would be $500 for that as well. So 500 for the first compound, 50 for each additional for each isotope.
Yep, so the pricing structure is the same for all three isotopes now. Used to, when we had to work with universities to get some of the specialty isotope analysis done, it was a little more for the different isotopes because of their pricing structure, but now that everything Sam does in-house, it's all one cost structure, so it makes it much more simpler for you guys. So thank you, Sam, for that. Okay, Alan, this next one is for you. Can this process be used for inorganic elements?
Yeah, well, it has been used, and we've done some studies on nitrate. That's probably the only inorganic one that we've really been looking at, and it's worked quite well with that, with looking at nitrate degradation in the field.
Great. Another one for you.
Sorry. I will add that there are labs that can do, we only do organic compounds at MI, but there are labs that can do lead, sulfur, that type of thing as well.
Yeah, okay.
Yeah, and we work with one of the universities that can do the sulfur analysis, so we can send you that contact information if sulfur is of interest for a project. Okay, this one is for you, Sam. Can you talk about sample collection? Is there anything necessary in sample management to be able to carry out this analysis?
Great question. Sampling is pretty much identical to 8260. We're looking at 40 ml VOA vials. They need to be HCl preserved. So what that does is it ensures that there's no microbial biodegradation between sampling and when it reaches storage. And we ask for 4 40 ml VOA vials per isotope. So if you're doing carbon and chlorine, it doesn't matter how many compounds. If you're doing both carbon and chlorine, we ask for 8 VOA vials. And then shipping on ice, we always say ship on ice, make sure that it gets to us at 4 degrees or below. And that really just ensures that the compounds don't leak out through volatilization. Because as many of you know, the delta values that we're measuring are unaffected by physical processes. So we just want to make sure that our concentrations match what we're expecting. Great.
All right, Alan, can you talk about any interferences that can be in the samples that could affect the analysis? Is there anything with hardness of the water or pH that could be a problem?
I haven't found any situations where we had issues with let's say hardness or other interferences in the water. I'm trying to remember now, but I could say I haven't run into any situations like that.
Great. All right. We do have a few more questions, and we're not going to be able to get to everything today. So feel free to reach out to Sam or to Alan if you want to send an email to info@microbe.com. We're just going to do one last question due to time. So the last question that we have, I think, Sam, would be a good one for you is, do clients have limitations on being able to access the online data? How do we get to that database? And how easy is it for them to speak to one of the MI scientists to get help with interpretation?
Great question. Anyone who receives a report, so if your email is attached to receiving the data for CSIA, you should have automatic access to the database. It is technology, of course, so if you run into any issues with that, reach out to me. I will ensure that we make sure that your email address is added to the database, and we can get IT on it if there are other issues involved. In terms of looking at the data and really analyzing it, we do offer comprehensive reports as a 15% surcharge of the analytical costs. But I'm also always happy to kind of briefly talk through the data with you, as well as help you work through the database itself if you need help with that. So it's very easy for anyone who has called MI. It's very easy to get a hold of a scientist, an expert in whatever analysis that is offered, and we're always happy to chat with you.
Yeah, like Sam said, we want to be part of your team. We know not everyone has a microbiologist on staff or a chemist that can help. This analysis is our specialty. So Alan is wonderful to help us, and we have Sam here on site. So if you have any questions, don't hesitate to reach out to us. We do want to help you. Thank you so much, Sam and Alan, for doing this presentation today. It was wonderful. As Sam mentioned, it's recorded. It's going to be on the resource section of the Microbial Insights website. You'll get a link. I know there was a lot of information presented today, so you'll be able to go back and take a look at that. If you think of other questions, or if there's questions we don't get to, don't hesitate to reach out to that info@microbe.com, and either Sam or Alan will get answers for you, and we'll get back with you on that information. But we really, truly appreciate both of you for taking the time and sharing all your years of expertise. You both did a phenomenal job, and we thank you as the audience for being here today and taking time to listen, and look forward to another presentation next month, and hope you'll join us. All right. Thank you, Sam. Thank you, Alan.
Thanks, Dora. Thanks, everyone.
Bye-bye.
Thank you.